Okay, this week, these 2 weeks coming up, we're going to discuss vertical motion, which is just another direction that the air is moving, stability, and then moisture. So think about the air. It can move in 3 dimensions. So we're going to think horizontal is typically the strongest dimension, has the most wind speed, but there can be very strong updrafts sometimes, and an air parcel can move in the vertical direction as well. When you experience turbulence when you're flying, if you see clouds, all those are examples of upward motion. So just looking a little bit at the speeds of these upward motion, say you're flying through a rain cloud, you might get a speed of about 10 feet per minute. Not a big deal, right? But if you're going through a severe mountain wave or really bad clear air turbulence, you might be moving at over 5,000 feet per minute, literally a mile a minute, like 60 miles an hour or more. And some severe thunderstorms have had wind clocks upwards of over 100 miles per hour. So you can see vertical motion plays a big role in what you're doing and how you're dealing with things. One of the issues with vertical motion, how do we generate it? Well, think about it. If you clapped your hands together, what happened to the air between your hands as they were moving together? Well, they had to go somewhere. And in the case of the Earth, since there's a ground underneath it, it can't go down, so that air would go up. It's called convergence. So if you do the opposite and push your hands apart, then you've got to fill in the gap where your hands were with air. Air's got to come down if you have the ground below you. And that's divergence. The air is sinking down. So those are the two main mechanisms that we get to move the air up or down. And they can show up very nicely sometimes in looking at surface weather maps, for example. Here we have winds popped around at a low that was over West Virginia at this time. Look at the winds out of the northeast here, 20, 30 miles an hour. Winds are coming in the other direction over West Virginia from the northwest, 20, 25 miles an hour. They're meeting here. Guess what? That air can't go down into the ground. So it's convergence that's happening there. It's being lifted. That's where all this precipitation and rain is occurring. It's even happening right along the front right here as well. So you can see topography actually plays a role in this. Think about the Appalachian Mountains. If you have a west wind, if you hit the Appalachian Mountains, that wind's going to start sinking when it comes down the east side of the mountains. So it goes up on the west side, if you have a west wind, and down on the east side. So east side, you might actually get some clearing and sunshine. The west side, you would have a lot of clouds and more precipitation. So topography plays a role in this as well. It can even be more of a role out in the Rocky Mountains and all. So moving along with this aspect of it, so let's take a look here at just some of that, what's going on right now in the atmosphere. And you can see there's a cold front out in the Midwest. And right here, all on that cold front, you have northwest winds on one side of it, southeast winds on another. You have a low pressure system. Guess what? There's going to be convergence right in there. So you're going to have vertical motion right in this area. And if you look at that, this is a parameter called moisture convergence, which is just combining convergence of the air and moisture. And you can see it maximizes itself right along this area. And actually, guess what? They're talking about putting a severe thunderstorm watch out for that area right now. So you can see in practice how you're using what you've learned here. So with that, we can move on to stability. Atmospheric stability is just another thing think about if you had a hot air balloon. A hot air balloon rises very quickly, and it rises because the air is lighter. It's actually warmer than the air around it. Warmer air is always lighter the longer as it can stay warmer than their surrounding area. So when you raise an air parcel up, if it's hotter, it's going to be lighter than the surrounding air. So what you're looking for when you look at these atmospheric soundings that I'm going to show you here, this is basically a temperature profile. A balloon went up. It measured the temperature this morning all the way up. The red line is just temperature. temperature goes to the right. So here's minus 10 degrees. You can see it intersects here. That's where minus 10 degrees is on the sounding. So with that, if you have no moisture in the air whatsoever, the air is going to cool at a given rate of 9.8 degrees Celsius for every 3,000 meters. So if the rate of cooling is that, and that's pretty steep right here, so it could be pretty close to that, then you're going to be, the air parcel that's being lifted, if it's cooling at that rate, is probably not going to be warmer than the surrounding air. It's going to be the same or colder. So if your air parcel is colder, it's going to want to sink back down. It's going to accelerate downward, actually. Now, if you get a parcel that's warmer, say your parcel is cooling at a rate of only 6 degrees Celsius per 3,000 meters. That parcel is going to be to the right over here. It's going to stay going up, 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 because it's going to accelerate upward until it finally gets colder than the surrounding atmosphere. So this is something with stability you've got to get a feel for here a little bit this week, and we're going to talk about it a lot in this week's lesson. You'll see it in your chapter and everything. So with that, remember one thing. Think about with stability is it's an acceleration. It's not just the air is getting pushed up at a steady rate. If you add instability to air that's already moving, it's going to pick up speed as it's going up. So instead of being 10 meters per 10,000 feet or whatever, it's going to accelerate and move faster and faster. The same will hold with the sinking motion. It will move downward the same way. So that's just some aspects of stability and what you're looking at. Now the next one we're going to talk about, we're going to start combining some moisture into this. Moisture can cause all kinds of problems with pilots because moisture changes state. In the natural range of temperatures in the atmosphere and the pressures, moisture will change from a gaseous state, water vapor, where you never see it, to a liquid state, and eventually to a solid state, such as ice or hail. So this change of state of moisture is really something that's very significant. In order to change states, if you're going from water vapor to a liquid, that requires a loss of energy by that water vapor. That water vapor has to be cooled in order to go that way because your molecules, think about it, your atoms, they move very quickly in a vapor. When they go to a liquid, they move slower, and when they go to a solid, they move even slower. So in order to lose energy, it means energy is being placed back out into the atmosphere, which is being heated then. The atmosphere is being heated by that loss of energy by that water vapor. It's called latent heating. And that release of warmth into the atmosphere can affect stability. Let's take a look at that sounding again right back here we were looking at earlier. And if I went in here and I said, oh, I'm going to lift this air parcel down here, but I'm going to saturate it. Well, if I'm saturating it, then it can't cool like dry adiabatically. It's going to cool moist adiabat, which is about 6 degrees for every 3,000 meters, for every 1,000 meters. So it's much slower, and that's going to be to the right. It's actually this dotted line right here. So the sounding is unstable. That air parcel will keep rising and accelerating upward. If something kicked it upward, like a cold front, which is what I'm going to show you right now, which is what's happening right out here at this time, then that's going to accelerate it upwards. And here is actually a measure of that instability. Right in here, these numbers, 3,500, are CAPE. They're convective available potential energy. The bigger they are, the better, more unstable the air is, the more potential for the air to rise if something starts it rising. So you can see right along here in this area from down here in Nebraska all the way up into Minnesota, you can see a very unstable air mass. You saw the moisture convergence there, so the air is beginning to get pushed. This is where they're going to be issuing a severe thunderstorm watch later today because of that impact of that air moving upwards. A couple other things about the change of state of the atmosphere and the liquid in it is all these gases exert pressure, and water vapor is another gas, so it exerts a pressure. There's something called vapor pressure for water vapor, and then there's saturation vapor pressure. If you know the difference, and saturation vapor pressure changes with temperature, so that the colder it is, the less the air can hold moisture. The hotter the air is, like you're down in Florida, for example, it can hold a lot of moisture. So the temperature at which it's going to become saturated will be much higher in Florida than it would be, say, in West Virginia in the middle of winter. Dew point's just another mechanism of looking at moisture. And relative humidity is just using the vapor pressure of the water vapor divided by the saturation vapor pressure to get what percentage of saturation the air is. That's relative humidity, how saturated the air is. Now, if the air is 100% saturated, you're probably going to start thinking about looking at clouds forming. So how does a water droplet form? Well, when it's got to be cooled, obviously, to get to that point. And there are things like dew that form on your airplane. Remember, we talked about conduction. Say your wings of your plane were very cold overnight, just sitting out there all night long and have been cooling. The air around them touches it. It's going to cool that air. You're going to get dew along your wings. Or if it's really cold, maybe you'll get frost. So it's something to think about that definitely can impact your flight dynamics and stuff when you're taking off that you want to be aware of. So with water vapor, we want to know how clouds form. Well, guess what? Water vapor, when it condenses into, evaporates and whatever, and becomes liquid, when it condenses, actually can't condense unless there is dust or dirt or sea salt in the air. It takes those to trigger what they call condensation nuclei. Otherwise, the relative humidity would have to be about 350% in order to get any droplets to form in the atmosphere. So instead, we have all the atmosphere contains a little bit of dust. All water molecules, water parcels, water droplets form and go around that dust. You also need things to trigger ice. And ice is triggered by ice condensation nuclei. They're pretty similar. They're not much difference. But ice will not form in the atmosphere until the temperatures are about -8 degrees Celsius. So you can have super cooled water from 0 degrees Celsius to -8. But once you hit -8, you start introducing these ice crystals, and you're probably going to begin to cool the water. Oh yeah, if you don't put them in, it can maintain just plain old water all the way to -37 degrees Celsius. So you can see these ice crystals make a big difference. But because they are in the atmosphere, most of a cloud by -10 will become all ice. So you can think of it as being snow parcels up in the atmosphere at that temperature. So most clouds, where the precipitation begins, are ice. Then gradually dropping down into rain as they get warmer. So METARs will give you the cloud height. They're measuring the base of the cloud, the bottom part of the clouds. And they'll also report the amount of the cloud at each height. So they basically also report a horizontal visibility, so how far you can see. Moisture, precipitation, fog, all of those impact this horizontal visibility. But METARs don't give the cloud type anymore. They used to. So you can infer some things, like if you have clouds below 500 feet and visibility below a half mile, you probably have fog, clouds right on the ground level. But then again, you could have clouds, you're seeing clouds above 20,000 feet, you're probably looking at cirrus clouds. Sometimes in remarks, you will see towering cumulus. So you'll know that there are cumulus clouds that may be developing into convective cumulonimbus clouds. One of the cool things when you're flying is you might be flying along a lake, say in the summertime, or even spring or fall. And maybe you see a line of towering Q, maybe 5-10 miles inland. What you're seeing is the sea breeze or the lake breeze. That's where the wind's changing direction. The wind's coming off the lake and going towards the lake on the opposite side. So that's where if you were landing along that area, be aware of that. You might have a wind direction shift there. And if you have instability, like we have talked about, you're going to get towering Q there and maybe even get some thunderstorms right along that wind shift line. So if you were coming in maybe to Myrtle Beach in the summertime and you saw this band of Q beginning to develop and you knew it on satellite and you saw it before you left and you knew you weren't going to land for an hour at Myrtle Beach, you might be expecting some thunderstorms to be around there at Myrtle Beach by the time you got there. Say you were moving towards flying south and you're heading towards, there's a big old warm front to your south. You're going to start seeing some high cirrus clouds, and if you're a jet, you're flying way up above those cirrus clouds likely. But maybe well to the south, you'll start seeing these big towers sticking out above the cirrus clouds. And they're thunderstorms usually right along the warm front or just to the north of the front. And there's a whole bunches of examples in this book this way. One of the things I wanted to show you just looking at satellite today, I was talking to you about Minnesota and the clouds and all coming right here. Notice this line of thunder showers and stuff to be developed right in this area where there's been heating and all that. There's a cold front moving through. Everything's coming together there to begin to merge in. You would have thought that it might be further east out here, but actually this is the area that they're looking at. Further back where the temperature's warmed up a little bit and all. So you can get a picture of where vertical motion is from looking at satellite, where moisture is. There's even a moisture channel, for example. And I can look at the water vapor, we'll say in the mid-level of the clouds, and I can see this moisture coming up right here and starting to rise up very quickly in this, right along this cold front right here. So you can see the moisture actually coming up out of the Gulf of Mexico here, and maybe even from the Southern Pacific and into this area. So you can actually track all this moisture you're looking at. So let me know if you have any questions this week. I look forward to hearing from you.